Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem number of dice rolls with target sum. Of course they would wait until Christmas Day to actually give us a slightly more difficult problem, but we'll try to make light work of this one. We're given n dice. Each dice has k faces that are numbered from 1 to k. So like a 6-sided die would be numbered from 1 through 6, but this time dices are going to be of arbitrary values, meaning like from 1 to k, where k could be bigger or less than 6. We're also given a target number, which we want to sum up to, given the n dice. And what we want to do is count the number of possible ways that we can roll the dice so that we end up with that target number. And it could be like the number of ways could be really big, so we want to mod it by this prime number. So initially this seems kind of like a combinatorics problem, a backtracking problem. And before we get into that, I think it's worth clarifying that in this second example, you can see that the number of ways to roll to the target 7, it does include duplicates, sort of. So the first way we could roll the first dice would be a value 1, the second would be 6, add those together, we get 7. But another way, the first dice could be 6 and the second one could be 1, that's also 7, and these are two different ways. So you can see that in the bottom left here and here. So that's worth keeping in mind, and I think that actually makes the problem more simple for us. So just thinking about this in terms of backtracking, what we want to do to enumerate all the possible ways is just go through every single possible dice roll. So these are the possible values for the first dice, and since we have 2 dice total, we would enumerate all the other possible ways. I'm not going to obviously draw all of those, but to get to the solution, this would be a valid path: 1 to 6, 2 to 5, 3 to 4, 4 to 3, 5 to 2, and 6 to 1. So all the other ways are not going to lead us to a result, but these 6 ways are, so the result is going to be 6. Now, as we are even going through this backtracking, what do you think we should keep track of? One is, of course, like the current target, because in a way, that's going to change. It's initially 7, but after we roll 1, the target does kind of update to now being from 7, but since we roll a 1, now what we're looking for is actually 6. And from like here, it's kind of the opposite. So we start with 7, we roll a 6, so now we're looking for a 1. So that's one variable we'll keep track of. Also, of this backtracking tree, we know the height is always going to be less than or equal to n, where n is the number of dice, because we're never going to roll more than n dice. So that's another variable we'll keep track of, what the current number of dice are. It starts out here, n is equal to 2, and then when we get after this roll, it is equal to 1, and then from here, if we were to go another recursive step, we'd get n is equal to 0, and that's of course going to be the base case. Now we have sort of a brute force backtracking solution, but we can actually optimize this via memoization, a dynamic programming technique. I won't write out the entire word. You could also just think of it as caching. That's the more simple way, because what you might notice here, looking at this picture, in our first example, like in this example, n is equal to 2, but suppose it's something else. Suppose it's 20. We roll 20 dice. Notice that this path, we took 2 dice and we ended up with a sum of 7. Let's say our target was actually something else as well. Let's say our target was 70. Well, after we roll these 2 dice, our new target, at least from here, becomes 63. And that's actually true for all of these positions. So even though we rolled different dice to get here, that does mean we're going to count all the possible ways from each of these paths. But once we go down this tree, we enumerate so many possibilities. The height of this tree is really, really big. We do a bunch of work to count the number of ways now that we can sum up to this target 63 with however many remaining dice. We know that the subproblem all the way over here is the exact same. Our target is the exact same. The number of dice we have remaining here is the exact same as over here. So why do all the repeated work here again just to end up with the exact same result? Well, we don't have to. Once we calculate that result here, we can store it in a cache. How do we define this subproblem though? How do we know if we find the same subproblem in different spots? Well, it has to do with the variables that we're keeping track of. For example, n, the number of current dice that we have remaining, and second, the current target that we are now looking for. If we ever find this subproblem in any spot, we'll know that this is something we already computed, and this is what we're going to store in our cache. This is going to be the key of our cache, and I'm going to map this to the count, the number of ways that we ended up with the target value from here. So that's pretty much all we need to know to solve this problem with memoization. In terms of the time complexity, since we are using caching and target, this is going to be the main part of the time complexity. How many possible values can n have? Well, whatever the input is for n. How many possible values can this have? Well, whatever the input is for that. So this is the number of unique ways that the recursive function can be called. But we know that within the recursive function, we will loop this many times, and this is defined by how many faces each dice has, which is another variable. So the overall time complexity is going to be big O, n times target times k. The space complexity is going to be n times target, because that's how many possible values are going to be in our cache. Now let's code this up. So I'm going to start by coding this up without memoization, without caching, and then we'll add that at the end because it's pretty easy to do. I'm going to start out with the mod though. It's 10 to the power of 9 plus 7. And I'm going to define a recursive helper function. I'm just going to call it count. And it's going to take two parameters, the number of dice that we currently have remaining, as well as what our current target is. And this is going to be called like this. We're going to return the count from here, passing in n, the parameter, and whatever the initial target happens to be. Now from here, let's start out with the important base case, which is always going to be if n is equal to 0. But just because we have 0 dice remaining doesn't entirely determine our return value. The main question now we have is, after rolling all the dice, were we able to reduce the target to 0? If we weren't, then we did not count a valid way. So what we do is, with a ternary operator, we can make this pretty simple. Return 1 if the target is equal to 0. We found a valid way to roll to the target. But if it's not equal to 0, return 0. It was not a valid way. If we don't reach the base case, we know we have at least one or more dice to roll. So let's roll those dice. Let's set our result. This is the number of ways that we're counting from this recursive call. Now, for the current dice, let's go through all the possibilities for the value. So it's going to be in the range from 1 all the way up until k. We say k plus 1 here, though, because k plus 1 is non-inclusive. It'll go from 1 to k this way. Now, we want to make the recursive call. So if we roll this value, then we can count now. For n, we're going to pass an n minus 1 because we just rolled a dice, so we have n minus 1 dice remaining. And for the target value, we of course are going to say target minus whatever the value was of the current dice. So this is the subproblem. This is going to return to us the count given that we rolled this value. And we want to take this and add it to the result. But we know we have to worry about the mod. So the easiest way to handle that actually is just to say, take this plus the return value from here and mod that before assigning it back to the result. So we can do this and then mod. And the reason we don't have to mod the return value from here is because, well, it's either going to be 0 or 1, or it will be returning the result, which we've already modded. So it will never exceed the mod. So adding both of these and modding it is sufficient. We can, from here, return the result, and this is basically the backtracking solution without memoization. And to add memoization, it's pretty easy. First, we declare our cache, and I'm going to use a hash map in this case. We know n target is going to map to the count, and now adding the base case here, if this has already been computed, if it's already in the cache, then return the value from the cache and using that as a key. If it's not though, let's compute it. And before we return, let's throw it into the cache. So storing it just like that. This is the entire code for the memoization solution. Let's run it to make sure that it works. As you can see on the left, yes, it does, and it's pretty efficient. In terms of time complexity, this is as efficient as we can get, but we can actually save additional space if we implement the dynamic programming or tabulation approach. And let me show you how we can do that. So looking at this tree, what we determined is that subproblems are defined by the number of dice and the target. So what we can kind of say is that for, let's say, n equals 1. And before I get into it, what we're doing now is actually called the bottom up approach. The previous thing that we were looking at was considered the top down approach. That's not super significant, but it does kind of make sense, and it does kind of help you understand these approaches that we're going to look at. You'll see why this is called the bottom up, because before, with the top down approach, we were actually starting with n equals n and then working our way down to n equals 1. But now with bottom up, we're starting with n equals 1 and we're working our way to n equals n. And you'll see what I mean. We're still counting the number of ways. So with n equals 1, the question is, what's the count? How many ways can we roll the value 1 and 2 and 3 and all the way up until the target, which in this example is just 7. So with 1 dice, how many ways can we roll the value 1? Just one way, right? Same thing with 2, same thing with 3, with 4, with 5, and with 6. With 7, we can't roll up to 7 with just 1 dice, so we can put a 0 here. One thing I haven't shown, though, is that we're actually starting from 0. And the reason for that doesn't become obvious until I probably show you this row, how we fill this out. And then you'll realize why we actually need to have this row filled in as well. From here, now we have 2 dice. So same kind of thing. With the second dice, we can roll the value 1, but we can't put a 1 here because with 2 dice, how can you possibly roll up to 1? So actually we say that, okay, the second dice we rolled 1. So in actuality, with 2 here, we can put a 1, because if we rolled a 1 here and we also rolled a 1 from the first dice, then we can actually sum that up to 2. But we also know that with the first dice, we could have also rolled a 2. Then we can put a 1 here. But with the first dice, we could also rolled a 4, so we can put a 1 here, and a 1 here, and a 1 here, and a 1 now in the 7 spot, because if with the first dice we roll a 6, and with the second dice we roll a 1, then we can sum up to 7. All these values that we filled out, we're only assuming that we rolled a 1 with the second dice. But what if we rolled a 2 with the second dice, or a 3, or a 4? We have to consider all of those possibilities. And so that's exactly what we're going to do. For every single value that we roll with any particular dice, we are going to, in the worst case, have to look at every value from the previous row. So you can kind of think of it the same way as the backtracking that we did, how we had to have like multiple branches and all that. And that's also why when we filled in this row over here, the values don't just come magically, because for every row that we're filling in, we have to look at the previous row. So with this row, when we fill it in, we're going to look at the n equals 0 row. And this one is not going to actually be filled entirely with zeros. Most of them are going to be zeros, but we're going to have a 1 initialized in this spot where n equals 0 and the count is equal to 0. You can think of that as like the base case. And the reason we're doing that is because then that'll make this math work out pretty nicely. Because now when we fill these values in, so if we rolled a 1 with the first dice, we would look at all of the previous values. They're all 0, so we can't really put anything here, but we see a 1 in this spot, so then we'd put a 1 here. And if we rolled a 2 with the first dice, again, we'd look, everything is 0, but there is a 1 here, so we'll put a 1 here. And that's how we'd fill in pretty much all of these. So that's the idea. Now, the last observation to make is we don't need an entire grid of memory like we did with the caching solution. We don't need two-dimensional memory because as we fill in each row, we only need to look at the previous row to fill in the next row. That's pretty much it. So we only need to have at most 2 of these in memory at any given point in time. And lastly, what do you think is going to be the return value? Well, in this second example, n equals 2 and target equals 7. So from this second row, n equals 2 row, we're going to return the value that's here because that tells us with 2 dice, how many ways were we able to roll the value 7. So that's what we would ultimately return. And this way we optimize the memory from being n times the target to just being the size of a row, which in the worst case is going to be the target. So we optimize the memory to be target. Now let's code up this solution. I'm going to declare 1 row of memory. It's going to be all zeros and it's going to be the length of target plus 1 because we want to be able to index the target value. So we need to make it target plus 1. And also the 0th value is going to end up being a 1 initially. And don't forget that what this represents is, for example, dp of I would be the number of ways to roll the value I, whatever that value happens to be. Let's also quickly have our mod. We're going to have several loops here because this is, again, not a time complexity improvement. So the first loop is going to tell us which dice are we on. How many times do we need to do this? Well, for how many dice we were given. This variable, we're not going to use it. I'll just tell you that. But now what we're trying to do is compute the next row. I'm going to call that next DP, and it's going to be initialized the same way. It's going to be all zeros. It's going to be the length of target plus 1. For this dice, we want to roll it. We want to get the value. So I'm going to say for val in range from 1 to k plus 1, this is kind of the same as before. So we rolled the dice. These are the possibilities. Now, the last thing, remember, we want to possibly look at every value from the previous row. So what you might think is in this loop, we can say for I in range, and this time I represents like the total, for I in range from 0 all the way up until target plus 1. And what we're trying to do here is find the value that we'd put at next DP. But what does the index represent here? It's the total that we get. But it doesn't really make sense for I to be less than the value that we rolled. I mean, I guess what we could say is I plus the value that we rolled, but that kind of gives us an index out of bounds, doesn't it? Like on some of the last iterations of the loop. So a better way to deal with this is to actually say for I in range of value up until target plus 1, because we know that the total that we roll can never possibly be less than the value. So this is the total, and maybe I'll just rename it that, the total that we've rolled. Now, for the index of this, we can just put the total. But what will this be? How many ways can we roll this total? Like, we need to count that. That's our job right now. Well, what we're actually doing here is actually adding that value to this index, because there might be multiple ways that we end up rolling this total value. Maybe there's one way to roll to this total if the dice value was 1. Maybe there's another way to roll to this total if the value was 2, etc., etc. So that's why we'd add here. But the way I'm going to write the formula is actually going to be different because, again, we need to consider the mod. So what we're going to say here is next dp of total plus something. And all of this is going to be modded. So now we just need to figure out the formula. What are we adding? Well, the number of ways to roll to this total, given that the dice value we just rolled was this, is going to be pretty much how many ways were we able to roll to the total minus the current value of the dice in the previous. So that's why we're taking the previous DP here. This is basically us looking at the previous row. So just to make this a bit more concrete, if we consider like some real examples, let's say, for example, total is equal to 8. And the current dice roll that we had was value is equal to 3, what we'd be asking is how many ways were we able to roll to 5 in all the previous dice rolls. That's what this is, because that count tells us how many ways we can roll to 8, because the value that we rolled was a 3, add that with this, and that tells us how many ways we can roll to an 8. So that's just to make things more concrete, because this is a pretty abstract formula, especially the fact that we have the index here is not trivial. That is the count. But this is pretty much the entire solution. So last thing for us to do is just to reassign DP to the next DP after every iteration of the loop. And lastly, the return value, like I said, is going to be DP, so the last row, at the target value. That tells us how many ways we were able to roll to the target value, and in this case, the target is the parameter itself. So this is the entire code. Let's run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.